The broadcast is now starting. All attendees are in listen-only mode.
All right, welcome everybody to the Think Big Analytics webinar, Introduction to HDFS and MapReduce. I'd like to thank you all for coming. This is our first webinar, first of many more to come. Hopefully you guys walk away with learning a little bit today. Yeah, let's dive into Hadoop and MapReduce. So a little bit about who I am. My name is Ryan Tabora. I'm a data developer at Think Big Analytics. So I'm both a consultant and a developer. I've got plenty of experience working with Hadoop, HBase, Hive, Solr, Cassandra, etc. We deal with this stuff every day. And just a little selfish plug here, I'm actually helping write the O'Reilly Definitive Guide on Lucene and Solr. That's scheduled to come out sometime around May. So if you're interested in search technology and search technology on big data, look forward to that. A little bit about Think Big Analytics. We're a big data consulting firm, mainly focused on things like Hadoop and Cassandra and NoSQL technologies, helping enterprise clients figure out how they can make value out of their big data. And that's not only in infrastructure and getting the data in. We also have a data science team that helps you figure out what you can do with your big data. So interesting stuff we do there. A little bit of background. Our founder and CEO formerly worked with Seabridge. And if you know anything about that, they've done some very interesting stuff and dealt with big data before a lot of people did. We've got over 40 clients. This slide's a little bit old, so I believe that number has grown significantly. We're based all across the U.S. We've got an office in Mountain View. We've got an office newly opened in Salt Lake City, in Chicago, etc. But we have consultants located all over the nation. And we recently expanded to Europe as well. Interesting little graph here. Forbes actually recognized us last year as one of the 2012 big data pure play vendors. As you can see there, it's interesting because we're actually the only services company on that graph. So that was a good mark for us last year. All right, so let's get into what we're actually going to talk about today. So to give a little bit of structure, here's the list of things we're going to go through. We're going to talk about big data, why it's important. I know many of you probably are already well aware of that, and that's why you're coming to this webinar to check it out. We're going to talk about the Hadoop ecosystem, so what components make up Hadoop. And then we're going to do a deep dive into HDFS, and then a deep dive into MapReduce. We're going to talk a little bit about the Hadoop Java API, and then we're going to do some conclusions. I've also got some extra material on Pig and Hive. We'll see if we get to that, see if we have enough time. So, big data. EFC did a big study a year ago about how much data is actually that we're dealing with at this point, and they're projecting that by 2015 we're going to have 7,910 exabytes. Now, that's kind of an unfathomable number, but basically this just shows you that all kinds of companies all over the world are just starting to figure out what the problem of big data is. These traditional approaches, using relational databases and things like that, tend to not work with this massive amount of data. So, that's kind of what Hadoop is all about, a new approach to dealing with big data. And kind of why is big data important? So a cool quote here, simple algorithms and lots of data trump complex models. This is really interesting because a few years ago, Netflix actually had a competition where users could submit their algorithms to figure out the best recommendation system for Netflix. And whoever the winner was won a bunch of money, something like that. And the last two finalists had very different approaches. The first approach was a group that had a very complex and very deep algorithm that focused on Netflix data and produced some really great results. The second group actually had a much simpler algorithm and incorporated data from both Netflix as well as IMDb. So they got extra things like who the directors are, who the actors are, things like that, maybe genre, and they incorporated that in their model, and they actually ended up winning the competition. So that's just a small example of where more data can help you out. And obviously, some of the pioneers in this industry, Google, Yahoo, Facebook, they've been dealing with these problems for a long time. Google indexing the web, I believe they're taking basically downloading the internet, twice a day. So that's a lot of data. And these groups are the first people that started figuring out how they could deal with big data, creating their own types of distributed systems that eventually led to Hadoop. So let's talk a little bit the Hadoop ecosystem. So what's the common tool that companies today are using to deal with big data? It's Hadoop. And Hadoop is basically a cluster-oriented distributed computing platform. So that means that we're talking about running not only on a single machine, but running on many machines in a cluster. And these machines are commodity server class hardware. What does commodity mean? So we're not talking about the computer you have in your basement that's falling apart or some Frankenstein thing that you've gotten from spare parts. We're talking about commodity server class hardware. So these are still server computers. Granted, they're not top of the line $1 million huge supercomputers. They're just commodity servers. So generally, what I like to say is, if you go into the store and you've got the good, the better, the best, and the cutting edge stuff, we're talking about the good to better range of computers. And finally, it's extensible. So as I talk about Hadoop as a platform or as a group of components, that's because there's many different components that run with Hadoop and run on top of Hadoop, and the community is expanding that number of components today. It's very extensible. So as I said earlier, Google was one of the first groups that had to deal with big data, and the engineers at Google actually created this thing called Google File System, which was a distributed file system very similar to HDFS. And since they pioneered it, they created a white paper on Google File System and MapReduce on top of it. And eventually, the open source community used that paper to create the open source version called Hadoop. So the other interesting thing to note here is that MapReduce wasn't invented by Google. MapReduce is a programming paradigm, and we'll talk a little bit more about that later. But Google made it famous basically by using it on top of their Google file system. So what is Hadoop? Again, so Hadoop is a platform, many different components inside of that platform, and it distributes and it replicates data across a cluster. It manages parallel tasks created by users. So, someone like me, a developer, is going to create a job. We're going to send that job, typically in the form of a jar, to Hadoop, and Hadoop will kind of parallelize that job across your cluster. Hadoop runs as several processes, as we'll get to know a little bit later. And finally, again, the Hadoop generally refers to a tool set, not a single tool. So we've got HDFS, we've got all these different things. And again, I'm going to get a little bit more into that later. And why is Hadoop interesting? Well, first of all, it handles unstructured, semi-structured, or structured data. And a lot of people say, unstructured data doesn't really exist. But the point is here is that, you don't have to talk to your database administrator to load your data into Hadoop. You can simply move your file into Hadoop. It doesn't matter what format it's in. You could just drop it in Hadoop, and that's a wonderful thing for a lot of companies. And obviously, it handles enormous amounts of data. Companies like Facebook are dealing with petabytes and petabytes of data, on a daily basis, and Hadoop can scale to handle that kind of data volume. It provides flexible data analysis and machine learning tools. So, if you ever heard of things like Mahout, integration with R, a lot of people are doing some very interesting data science, statistics type work on top of Hadoop. And again, since we have all this data, the potential is limitless. And finally, we've got cost-effective scalability. And we're going to talk a little bit more about this later in detail. But basically, what this means is that your power and your power of your cluster will scale linearly. So the idea is that you can just add more nodes to your cluster, more commodity nodes, and we're not talking about supercomputers, more commodity servers to scale linearly. And that's obviously cost effective because you're not having to buy, an amazing brand new supercomputer every time you want to get more power. So the Hadoop ecosystem. Here's a list of what I consider some of the core components of the Hadoop ecosystem. Obviously, there are many more outside of this, but these are some of the ones I'd like to focus on today. And the core components here being HDFS and MapReduce. And we'll talk a little bit more about these definitions as we go into them. The first component we're going to talk about is HDFS. So what is HDFS? Well, it's the Hadoop distributed file system. It's exactly what it sounds like. It takes your files and it will store them in blocks across many nodes in a cluster. And generally these blocks are pretty large in comparison to other file systems. So, a typical file system might store blocks in size of 4 kilobytes or 8 kilobytes. But HDFS stores blocks in sizes of 64 megabytes by default, or even larger in some clusters. In addition, it replicates the blocks across the nodes for durability. So, you've got your data spread across this cluster, and depending on your replication factor, you can set the number of times you want those blocks to be duplicated. So, say if one of your nodes goes down, the data still exists on another node. And as we'll learn a little bit later, this also provides for some data locality when you're running your jobs across the cluster. So instead of shipping, your data to a process on another computer, Hadoop can find where the data is and run the process on top of it. And since it's replicated, there's many different options it can look for the data. And finally, it's got master-slave architecture. So that's pretty straightforward, and we'll get more into that a little bit later. HDFS traits. So the first one here I'd like to point out is that it's not fully POSIX compliant. And you can think of a POSIX compliant file system as one like Mac OS X. So POSIX is basically a set of characteristics of a file system. For example, I should be able to copy my file, I should be able to edit my file, I should be able to do all these different things. And that's basically what defines a POSIX system, like Mac OS X. Hadoop HDFS is not like that. So first of all, it doesn't provide file updates. And that generally tends to lean towards types of patterns where you're going to write once and you're going to read many times. So you shouldn't expect to do any kind of like transactions or something like that inside of HDFS alone. We leave that to maybe some other things that we can get to later. But inside of HDFS, since you can't update, you're generally going to write everything once and then read it many times, maybe in the form of MapReduce. And again, so we've got large blocks, and they did it this way because they intended for users to have sequential read patterns. So they expect you to read that 64 megabyte chunk all at once. And generally your jobs are going to go over much more data than that. So it's generally not a problem, but it's something to think about, is that when you're running these jobs, you don't want to be running it over little bits of data spread across all your blocks. It's generally meant to read the blocks entirely in a sequential manner. And finally, it's designed for batch processing. So, when we're talking about running jobs on top of HDFS, we're generally talking about jobs that may take some time and they may be scheduled every few hours or something like that. It's generally not kind of random access to HDFS. And again, there are other things that can address that issue. Something like HBase, but we'll get to something like that maybe in a future webinar. So I previously stated that Hadoop is run in a master-slave architecture. Let's talk about some of those processes that are HDFS. So the master processes we have here, first of all, we have the name node. So the name node will basically hold the metadata that describes where the blocks are in your cluster. So if you've got a file inside of HDFS and you want to read that file, the name node will tell the client, well, this file has blocks 1, 2, and 3, and they're on nodes A, B, and C. So It's very important that the name node stays up, because obviously if the name node goes down, you've lost all of those references to all those blocks, which means you can't read the data anymore. So the name node is generally defined as a single point of failure. And that's why we have the secondary name node. Now, maybe I shouldn't say it that way, because it's important to note that the secondary name node is not a hot failover. So if you completely lose your name node, there is going to be some manual intervention and most likely some downtime. The secondary name node basically holds a copy of the name node metadata. And again, it is a manual process to get the name node back up. And then we've got the slaves, so the kind of worker nodes, and these are called data nodes. Data nodes are generally run across all of the nodes on a cluster, and they're responsible for the grunt work of the cluster, the block creation, the deletion, the reads, all that kind of stuff is run by the data node, and the data node takes orders from the name node, as it makes sense. So, thinking about this, I like to put it in picture format because it's a lot easier for me. So I've got myself there coding away. And my job is to put a file inside of HDFS. So I'm going to talk to the name node, and the name node is going to tell me, okay, well, let's split the blocks in these ways. So here we got an orange, pink, and green blocks. And the name node is also going to tell me where I should put those blocks. And that's exactly what I do. So the client is going to write those to those 3 data nodes. And the name node is going to keep the metadata that says orange is on the first data node, pink is on the second, and green is on the third. Okay, and then these data nodes are basically going to replicate. So the data node 1 is going to talk to data node 4 and 6 and copy those files over to those nodes. And same thing with the pink, and same thing with the green. So as you can see here, the name node has all that metadata. If we ever want to read it, we can. But that's simply it. So now, what if I want to read this file? So makes sense. I'm going to talk to the name node. I'm going to say, where is the file that I just put? Where is file 1? And it's going to give me the blocks 1, 2, and 3. It's going to say, look on data nodes 1, 2, and 3 for blocks orange, pink, and green. So I'm going to try and contact those data nodes and start reading those files. But oh no, we've lost data node 1. What do we do? In terms of HDFS, not a big deal. We've got another one on data node 4. Data node 4 is going to make sure that it's replicated on data node 5. And then we're going to read those files. Another thing that I should mention here that I kind of missed on the previous set of slides is that Hadoop is also sort of rack aware, in the sense that you can tell Hadoop where your racks are, so you can kind of create a sense of where data should go. So let's just go back here. So here's the beginning of this slide. We can see that Hadoop let's say that the racks are 1 and 4 is one rack, 2 and 5 is another rack, and 3 and 6 is another rack. So we've got vertical racks here. Hadoop makes sure to put 1 inside of the rack so that to decrease network traffic, and it puts 1 outside of the rack so that if we lose that entire rack, we still have another replicate on another node outside of the rack. So that's interesting. We got to go through these slides again. Boom, there goes our node. And we still have the one on 4, and then we read the file. So the interesting thing there is the read time is determined by the transfer rate of the individual node multiplied by the number of machines that block is split across. So that's why I've got that little star there. The number of machines is defined by the number of machines that you're retrieving from. So our file was split into 3 blocks, so it was 3 machines. And that's a pretty powerful concept if you think about it. So if everyone's got 100 megabyte per second transfer rate times 3, that's 300 megabytes per second. Now let's think about if we've got tons of data spread across, this cluster. So let's say every time we're able to get blocks from every data node. Now, if we want to have 1,000 megabytes per second transfer rate, we can just add 7 more nodes. Something like that, we'd have to pay a lot of money for in a single machine. So when I'm talking about linear scalability, that's exactly what I'm talking about. The ability to add additional nodes and increase the power of your cluster. So How do we access HDFS? Well, the easiest way to do it is by using the HDFS shell. And basically, the shell is just a command line interface that you can access through the terminal. It allows you to create, copy, move, delete files, do administrative duties, etc., set replication factor, all kinds of stuff. So I thought it might be interesting for me to just show you what it looks like. So let's take a look at the terminal and see what it's like to put some files in HDFS. So as you can see here, I've already got some stuff there. I was making sure it works before I did this. But the first thing that we'll do is we'll just take a look at what I have inside of Hadoop right now. So I've got it running locally on my machine here. As you can see, we've got 3 folders: output 1, temp, and user. So let's create a directory. Let's call it books, because I've got some books files that I want to put in there. So if I look on my desktop, I've got a few books on here. I've got Pride and Prejudice, Huckleberry Finn, okay, and Les Miserables. Might have pronounced that wrong, my apologies. But let's put those books inside of HDFS. I'll show you how simple it is. Just like that. Boom. No talking to my database administrator, no creating a schema file, nothing like that. There's books. There are my files, and I can even read one. Let's just do this. Cool. So, it's that simple. All right, back to the deck. So that was HDFS. Let's talk about the next one in our Hadoop ecosystem called MapReduce. So MapReduce, it's all in the name. We've got mappers and reducers. Again, MapReduce is a programming paradigm. So when a developer is using MapReduce, they're going to create a map and a reduce function. And they're going to compile that as a jar and send that to the Hadoop cluster. And like I said earlier, Hadoop will handle distributing those tasks across the cluster. And similarly to HDFS, MapReduce is generally batch-oriented. You'll find as we run this job that I've got set up for the next demo that it takes a little bit of time, maybe a little bit more than you would expect on such a small set of data. And that's because there's some overhead in setting up the job and sending out the map and reduce tasks to different nodes. So for that reason, it's typically a batch-oriented programming paradigm. And similarly to HDFS, we've got master and slave tasks that run MapReduce. The master task is called the job tracker, and basically it manages the MapReduce job. So when you send your jar, you're going to be sending it to the job tracker, and it's going to figure out which nodes to send the tasks to. And like I mentioned earlier, it's going to look for data locality. So it's going to try and send the correct tasks to where the data is. So you don't have much network traffic of shipping data from one node to where it needs to run on another node. And then also, if we've got task failure, so if one of these tasks fail on one of these nodes, just like we lost that machine in our previous example, it will make sure that that task is running on another node. And then we've got our slave process, similar to the data node, which actually does the work. It gets the MapReduce tasks, it creates the individual MapReduce tasks, it runs them, and it reports its status back to the job tracker. So, for pretty much every programming language, we've always got the hello world. In MapReduce, we've got the word count. So let's actually take a look at the flow of a job and look at the logic of how it works. Because to me, it's the easiest way to understand how MapReduce works. So what we want to do here is convert the input to the output. So on the input side, I've got 4 files, similar to my book files. And the input, the first one has Hadoop uses MapReduce as its text value. The second one has there's a map phase, and the fourth one has there's a reduce phase. And we want to change that to a word count. So we've got A has 2, is has 2, etc. So how are we going to do that? Well, we have to use our mappers and reducers to do that. So as we can see here, we've got a map framework, and it's important to note that MapReduce works in terms of keys and values. So it's going to take a set of keys and values, do some work on it, sort and shuffle it. Basically, the same key is going to go to a reducer. And again, we'll go into this because I know that's a little bit confusing the way I'm saying it. And then we've got our output. So let's take a look at the mappers here. So like I said, we've got keys and values. We'll say here that the keys are just the name of the document. In actual MapReduce, the default file format is going to give you an offset into where the file is into Hadoop, but that's not really important. Let's just think in terms of the key is the document name and the value is the actual text inside of the document. So for the first document, key is doc1, value is Hadoop uses MapReduce, and so on. And basically, what these map tasks are going to do is break that string apart into tokens and output the number of times it's seen it. So the first one outputs Hadoop 1, uses 1, MapReduce 1. It also looks like it's lowercasing everything here. Excuse me. And then we've got the second document there is a map phase with all 1 tokens. So if you could visualize it, that map task is simply splitting the string and outputting each token. And then, like I said earlier, we've got the sort and shuffle phase. And basically what happens here is we define on the reduce side kind of a partitioning scheme. So we see that the first reducer has 0 through 9 and A through L. So that means that any keys from the mappers that have that start with the 0 through 9 or A through L, they're all going to go to that first reducer. Any that start with M through Q are going to go to the second, and R through Z for the last. So this kind of this sort and shuffle phase that sorts and shuffles the data to different reducers based on this partitioning scheme. So this is what the reducers are seeing. So they see a key and a list of values. So we've got A with 2 different ones, 1A coming from the second input and 1 coming from the fourth input. And basically what the reducer task is going to do is simply iterate over that key list value group that they have. So reducer will say, for key sum plus 1 for each one that it sees. So, and then we've got the simple output there. A2 Hadoop 1 is 2. So kind of looking at it, the mappers transform 1 input to 0 and key value outputs. And the reducers will basically gather them, collect multiple inputs to 1 output. And I don't want to go back because I'm actually going to have to go through that entire process again. But the reducers basically take many key value pairs and output 1 kind of aggregated view of the output. So similarly to HDFS, I want to kind of visualize what this looks like on a cluster. So you see we got the name node, we've got the job tracker, task tracker, data node, and we've got our file split across those 3 nodes. And me over there, I've created a MapReduce job. We can think of it in terms of word count or whatever it is, but basically I've defined a map task and a reduce task, and I'm submitting that to the cluster in terms of a jar. So the job tracker is going to get that, and it's going to determine where it can send, where it can create those those tasks. So it finds the data across all the 3 nodes, and it says task trackers create those map tasks. So the task tracker creates the map task, and then it uses those blocks on those nodes as its input. And this is called the map phase. And the mappers are going to create those key value pairs. And it's important to note here that the intermediate data is stored locally, so it's not stored in HDFS. It's actually stored in the local operating system. And once it's created those key value pairs, and as you see, I've kind of got them color-coded. We've got a blue pair, we've got a purple pair, and we've got a brown pair. We're going to go through that sort and shuffle phase and move all of the correct keys to the correct partitions. So you see there where that blue one moved over to the first node and the purple one moved over to the second node, and the brown one stayed where it was. And the reduce tasks are going to work on those key value pairs. And here it's creating the output local to each node. So if you're running a big MapReduce job, you'll see that you have many different outputs. And actually, I'm going to run a job in a second here so you can see what it actually looks like. But each reducer is going to create its piece of the output. And that's pretty much it. So let's take a look at what that actually looks like, on my local setup here. So let's see here. So we just uploaded all those books to HDFS. So I've actually got a command pre-baked here for that. So here we go. So we say Hadoop jar, and then I've got this path to this jar that's actually provided in the Apache download with a bunch of examples. Hadoop jar, path to my jar, word count, input path to my books, and output, where I want to see my output. So I'm going to put it as output 2, since I've already tested this, and this is going to be a new folder. So here we go. We can see we've got map and reduce at 0%. And while this is running, I want to kind of take a look at the UIs that Hadoop provides you with. So we've got a name node to kind of monitor HDFS and see what that looks like. And then we've also got the job tracker interface. And as you can see here, we can monitor these jobs that I'm running. So this is the one that's currently running, word count. You can monitor what maps, how many maps we have, map percent complete, etc. It's a very powerful tool for debugging. And okay, we see that our map phase is complete. We can actually click into here and we can look at, okay, so there was 3 map tasks. We can look at the details for each one. So there's some very cool stuff that Hadoop provides right out of the box. All right, so it looks like it's finished. Map and reduce 100%. Job complete. Good news. So let's take a look at what we have inside of HDFS. So you can see that part R00000. That's because I'm running this just on a single node, my little MacBook here. That's why I've got one reducer output, and we can actually, oops, we can actually look at those results like this. There we go. So we can see the counts for all these different words. We've got plenty of thes. So obviously we can make this much better by kind of ignoring those type of words. Or we've got so and so comma. That was tokenized that way. Many different improvements we can make here, but pretty cool. Let's go back to the deck. So now I want to show you what the Hadoop Java API looks like. So same exact thing that we logically walk through. Let's take a look at what it actually looks like into the code. So we've got a lot of stuff here, and I'm not going to go into every little detail, but we'll take it step by step. So first, we have the definition of the class, simple word count mapper. And basically, it's implementing a mapper where it's using the key value format there. So the key for the input is long writable, the value is text, and the key for the output is text, and the value is int writable. And then here we're creating some different types to hold our data. I'm not going to get too deep into this here, and so we'll just kind of skip over that. But basically, we're just creating the data types that we're going to use to store our data. And then here I've got my actual map task. So as you can see in the constructor, we've got long writable key, value, text, document context. And then we've got this output collector, and that's what we output to. And it's got the key, text, and value int writable. And then finally, we've got a reporter. And we don't have to worry too much about that. The important pieces here are the key value pairs. And as you can see, basically what I do, like I said earlier, is split up the document context. So we're splitting, there's a little regex there, splitting on white space. And it says for every token in that string that we just split up, we're going to lowercase it and output it to the collector. That the word itself, the token, is outputted as the key, and 1 is outputted. So every time we see a word, we just output that as the key and 1 as the output. So yes. And here's our reduce code. So just like our mapper code, we've defined our key value pairs. So our input here is going to be text. Our value is going to be int writable. The output key is text, and the value is int writable. So let's take a look. So we've defined our reduce, similar again. We've got key is text, and then we've got a list of int writables as our counts. And then we've got a collector here so we can write our output to HDFS in terms of text and int writable. And again, we've got another reporter object. So basically, it takes a count, sets it to 0, and it says while counts for that key has another one, let's increment the total count. It's as simple as that. We go through, and then we output the key and summed count. Looks like I got an extra slide here. So, like I said, there's more to Hadoop than just HDFS and MapReduce. We've also got Hive, Pig, and HBase. Just for a quick overview, Hive is basically a SQL-like syntax that users can use to create MapReduce jobs. So it's very powerful for business analyst types who are very familiar with SQL, but can't really get into the deep Java code that we wrote. That example that I just gave you, that's pretty much as simple as it gets. So I know that looked a bit complicated and a bit scary with all the different ways that we created the job, but that's why we've got Hive. Hive allows you to do SQL-like commands, and it will create, as it can, the most optimized MapReduce job on top of data. So that's very cool. Pig is very similar in the sense that it's another type of dialect that you can use to create MapReduce jobs. And this is more of like a scripting type, so you find a lot more of developer types using Pig. It's also kind of more of like a step-by-step kind of language. So you find people using Pig for things like ETL or something like that. But essentially, it's just another kind of interface into MapReduce. And then finally here, I've got HBase, which is a NoSQL non-sequential data store. So if you're looking for that kind of random access, kind of real-time access to your data that lives inside of HDFS, you can use HBase for that. So I got some little animations there that I didn't use. So in conclusion, what have we learned? Hadoop is a cost-effective, scalable way to store massive amount of data and perform arbitrary analysis on those data sets. So as I said, it scales linearly with these commodity nodes, which is a beautiful thing. And you can store lots of data without worrying about losing it, since we've got that replication factor. And then, basically, the power of MapReduce is limitless. You can do whatever you want as long as you can put it in that MapReduce paradigm of key value pairs. And Hadoop tools, there's tons of tools. So we've got many more outside of that list of components. Some very interesting ones coming out there, like Impala from Cloudera, HCatalog, all kinds of really cool stuff that's being built on top of Hadoop, and it's growing every day. So it's a great thing. Another point that I should point out here is that there are many different distributions of Hadoop. So we got things like MapR, we've got Cloudera, which I just mentioned, and we've got Hortonworks, which are all different distributions. And we've also got the Apache. So the Apache is, the free open source version that generally people start out with. But these other distributions provided by Cloudera, Hortonworks, MapR, and more are provided to basically provide a distribution. So sometimes you'll have issues running different versions of things. Since it's an open source community, some of these versioning issues tend to cause a lot of trouble for operations type people. So having these distributions from these providers is a really nice thing, because you get a set of components that will always work from each other. Also, they're supported, and some of them also have some pretty cool features built on top of Hadoop. So I want to thank you all for coming. My name is Ryan Tabora. Again, you can contact me at ryan.tabora@thinkbiganalytics, or you can contact our solutions consultant. If you have any questions about what maybe Think Big Analytics can do for you, he's a great person to talk to. His name is Matt McDevitt, matt.mcdevitt@thinkbiganalytics.com. You can check out some of our future webinars at thinkbiganalytics.com. I know we've got a few here. Let's just take a quick look at what we've got coming up. Let's see here. I lost these resources. All right. I'm not sure where we've got these here. We used to have a little, there we go, webinars. So here was mine. And then we've also got one with Jeffrey Breen coming up here by using R with Hadoop. So if you're interested in kind of data science and what kind of analytics you can do, please tune in. It's Thursday, January 24th at 11 a.m. PST. And we've also got this the business value of big data by Jeff Kelly of Wikibon on January 17th. Feel free to check those out. And I'm probably going to do some more in the future as well. So keep your eye on thinkbiganalytics.com. We're actually going through we're redoing the site in a little bit, so it'll look a little bit different. But keep your eye on this because we got some interesting stuff coming down the line. And anything else? Yeah, so if you guys want to see the slides, I've got them on SlideShare. You can find me. My username is RA so slideshare.net, RA Tabora presentations. You can see here. Here's our link to our presentation. It's got everything in there, and you can check it out. And last but not least, feel free to contact me. Find me on Twitter, wherever it is. Ask me any questions. I'll gladly help you out. I hope you guys all learned something today. I really enjoyed it, and take care. Thanks, guys.